Okay, I begin by thanking the organizers for giving me this wonderful opportunity to present my work here. So there is a slight rephrasing of the title, but content is same. And the work is done with Siddhartha Mukherjee from IIT Kanpur, Samriddhi from here at ICTS. Now the talk will feature dense bacterial suspensions. So the main theme is you start with a non-uniform distribution of bacterial activity and allow it to mix via advection and diffusion and look at various flow features. So I will come to the details in a bit. So before that, I just give you a preamble of what active matter is. These are systems that are composed of agents that can consume energy and have exhibit directed motion. So these are out of equilibrium systems. Now, they span a range of scales. At the meter scale, you have these schools of fishes or flocks of birds, and at the micron scale, you have these microtubules or dense bacterial suspensions. Now, perhaps the earliest work in this direction of dense bacterial suspensions, which also indicated turbulent, chaotic flow features, was by Wensing et al. They performed an experiment in quasi 2D with Bacillus subtilis bacterium and found that the suspension exhibits these chaotic features. And if you analyze the local motion by PIV imaging, you will see that these vortex structures appear. Now, how do we model these things then? So these turbulent structures, these allows a generalized continuum hydrodynamic description. So they also wrote an Navier-Stokes-Lake evolution equation for the coarse grained velocity field of the bacteria. Now, there are two main ingredients here. One is this term, which is the toner 2 term. There is this green overbird. Here, for alpha less than 0 and beta greater than 0, it will show a flocking like global ordering. But in dense suspension, we don't see global ordering, so there must be some instability mechanism, and there comes this Swift-Weinberg instability term, this brick red underbar. And the combination of these two will generate vortex structures. Here you see two videos. In one case, you have this alpha, this activity, which is the essence of this talk. Here you have this uniform activity, and here you have coincident heterogeneous activity, but both are constant in time. And you see these vortex structures, which looks deceptively similar to the experimental observations. And here are some works on this coincident heterogeneity, some experimental, some numerical works. Now, till this point, activity was considered constant in time, but there is no reason to think that or believe that, because like in many experiments, like in microreactors, you need mixing to homogenize those reactants, and mixing always happens from a uniform, from a non-uniform distribution of activity. Now, in that micron scale, only diffusion cannot enhance the mixing process, and it's hard to control this diffusion. And active fluids comes to the rescue. They enhance the mixing process by continuously stretching, folding the fluid elements. So here we propose a model where instead of keeping this alpha constant in time, we allow it to evolve via this advection diffusion equation. And mind you, this is a two-way coupling model. This activity is responsible for the underlying turbulence, and then turbulence this modifies, this shapes and this activity. Here is some recent experimental work with kinesin and microtubule mixture. So initially the flow is quiescent, and then you illuminate UV light on the left part, so this region will become turbulent. Then as time evolves, you will see that this active-inactive interface will propagate until the flow reaches a uniform state. Now here is some numerical simulation. So initially you initialize the system with a high activity at the center and quiescent region outside. Then as you evolve the system, you will see that this active scalar part here, these fingering structures will appear, which also you see in quiescent active matter systems. And this is the vorticity field, where the initially coherent structures will lose their signature and become uniform across the domain. And this is the gradient of the scalar field, where you see these tubular structures. I don't know if it's visible or not. And which are basically a reminiscent of scalar dissipation field in turbulent flows. Now, if you want to know how the homogenization happens from non-uniform to uniform activity, you can look at the probability distribution function of this scalar field. And initially, it is bimodal, and as the flow evolves, one of the ends shifts towards right, and ultimately it will reach a unimodal state. Now, in turbulence, we are always interested in what are the spectral features of the flow. So, in uniformly constant alpha, when it is not evolving time, then earliest work by Samriddhi's group itself, they have shown that beyond a critical value of activity, there is a universal state appears. So, this spectra that appears here beyond alpha, critical alpha minus 5, and below that things are non-universal, and that corresponds to somewhat weakly active turbulence. Now, in our case, the situation is much more complicated. Here, first of all, you have this non-uniform alpha. Second of all, it is allowed to evolve in time. So here we see the signatures of both these weakly active and strongly active regions. On the left part, you have this non-universal regime, and on the right part, there is a slide like this universal scaling k to the minus 1.5. And as the flow evolves, this energy spectra, first this crossover scale shifts towards left, and after that it shifts towards right. So how do we understand that? Since this is a two-way coupling model, we can look at the active scalar field. And initially, since the turbulence is very strong inside this patch, it continuously stretches and folds the fluid itself. And this crossover scale is somewhat related to that stretching length scale. And as the activity spreads, the turbulence becomes weak, and you start to see this universal regime shrinking. We can also look at the variant spectrum of the scalar field. Initially, you see that k to the power minus 2 scaling, which is reminiscent, like which you in general expect to see because of the interface. There is a discontinuity. And as the flow evolves, there are two scaling regime emerges. One is k to the power minus 4 at small k. That means the flow is becoming smooth at the larger scales. And then you see k to the power minus 1 kind of scaling. It will depend on the Schmidt number that you use. This is reminiscent of like Batchelor scaling in passive scalar turbulence. Now let's move on to the next case, self-similar fractal front growth. Now turbulence, what it does is it crumples the active-inactive interface. So here are three interfaces for different Schmidt number. As Schmidt number decreases, the interface becomes smoother and smoother. And here you see by box counting algorithm, you can find the fractal dimension, which after a transient time attains a somewhat steady value. And this is how the fractal dimension varies with the Schmidt number. Now, to summarize the talk, this advection diffusion model, it is quite effective in mixing, because if things are diffusion dominated, then mixing will be like will be dominated by diffusion process. But here it is super diffusive. And the next thing is activity field here shows some features like finger-like structures, which you generally observe in proliferating bacterial colonies itself. So, yeah, thank you.
Thank you.